You're welcome to my channel once again, still on acid-base disorder. But today, the focus will be on renal control of acid-base derangement. And this will form part 6 of 7. Let me quickly brush over some facts here that respiratory and renal system will respond to acid-base derangement differently. While the respiratory system will respond fast enough, the renal system response will be very slow. CO2 and carbonic acid will be controlled by the respiratory system. The renal system is expected to handle the bicarbonate ion control. In metabolic derangement, respiratory system is expected to compensate, and that could be done very fast enough within hours. However, in respiratory acid-base derangement, the renal system that's expected to compensate with metabolic shift will not do that fast enough like in the respiratory control. It will be done, but very slowly. It could take days. How will kidney help us to handle the acid-base derangement? The kidney is saddled with responsibility to control the bicarbonate ions. Decreased level of bicarbonate ion means metabolic acidosis. You know that already. The renal tubule has antipod mechanism, and that will allow sodium in and hydrogen ion out. Chloride ions can neutralize the positively charged ions. But when there is loss of chloride ions, it means the kidney is forced to reabsorb more bicarbonate ions. In renal cells, what are we going to find? The renal cells will produce bicarbonate ions that can be shunted to peritubular capillaries. Remember, at the capillaries will be CO2, and in the presence of water, carbonic acid will be formed, which can later dissociate to hydrogen ion and bicarbonate ions. That is, carbonic acid will dissociate to hydrogen ion and bicarbonate ion. The hydrogen will be released. The bicarbonate will get into peritubular capillaries and then into the blood circulation. The hydrogen that is released can be excreted, or it can form part of the water molecule and be reabsorbed. In the filtrate, the hydrogen could bind to sulfate, could bind to phosphate, or could bind to ammonia. If more of the above is the case, then hydrogen ion will not be available for CO2 to form carbonic acid. Carbonic acid is expected to dissociate into bicarbonate ions and hydrogen ion. Therefore, there will be less bicarbonate ions, meaning more metabolic acidosis, when the hydrogen keeps binding to sulfate, phosphate, and ammonia. What is the role of potassium in all this trouble? Potassium can compete with hydrogen ion. When potassium competes with hydrogen exchange with sodium, then the equation will shift. Raised level of potassium means less hydrogen in the filtrate. And when there's less hydrogen in the filtrate, that means we'll have less bicarbonate ion later on. And less bicarbonate ion means more acidosis. TK is associated with hyperkalemia and metabolic acidosis. And remember, once you have the potassium corrected either via hemodialysis, the acidosis will be corrected simultaneously as well. That is the reason that in DKA, we don't usually rush to give bicarbonate ion unless we are not getting potassium corrected on time and the acidosis is horrible, getting to the neighborhood of 7.1. In summary, in the cell, water will combine with carbon dioxide or carbon dioxide to form carbonic acid, and that will lead to the release of bicarbonate ion into the bloodstream and the hydrogen ion into the lumen. In the lumen, the hydrogen ion will combine with bicarbonate ion to form carbonic acid, and later on, the carbonic acid will break down to water and carbon dioxide based on the equilibrium shown down here. Now, CO2 with water leading to carbonic acid, and later on we'll have hydrogen ion and bicarbonate ion. And the equation could go either way, left or right, depending on the concentration of the reactants. Bicarbonate ion will be low in the face of Acidosis disease, chronic renal failure, carbonic anhydrase impatience by carbonic anhydrase inhibitors like acetazolamide, diarrhea leading to excessive loss, chronic nephritis, diuretics use, decreased aldosterone, increased ketones that will bind bicarbonate ion in filtrates and prevent its conservation. With that, I've come to the end of this very presentation. This is part 6 of 7. We have one more to go. Thanks for listening. Remember to share. Remember to subscribe so that you can get more of my presentations immediately they are published. I appreciate it.